Welcome to iLecture Online, and here's a really good example of how to utilize what we've learned on rotational motion on this very nice problem right here. So let's read it together. It says a grinding wheel starts at an angular speed of 20 radians per second. It is then allowed to accelerate at 25 radians per second squared for 3.5 seconds. The power is then turned off, after which it turns through 380 radians before coming to a stop. What was the total angular distance covered? How long did it take to stop? And what was the acceleration when slowing down? That's quite a problem, and after you read it, you probably don't know where to begin on a problem like this. And so the best thing to do is to write down everything that's given, everything that's being asked for, kind of make a drawing or a sketch if that helps, and kind of organize the problem a little bit. And it sounds like there's two parts to the problem. The first part is when the wheel is speeding up, and the second part is when the wheel is slowing down. So let's think about that. So I have a rotating disc. And there's two parts to the problem, part 1 and part 2. Here we're speeding up. And here we're slowing down. So what do we know during the speed up part? That the original omega is equal to 20 radians per second. The acceleration alpha is equal to 25 radians per second squared. The time, 3.5 seconds. And what are they asking for? What was the total angular distance covered? So theta, in this case, is unknown. So we'll put that down. All right, so for the first part of the problem, we don't know to what angular distance the wheel turned, and so we need to figure that out. For the second part, where we're slowing down, the angular acceleration is not known. I believe that's what they're asking for in part C. The time is not known. The initial omega is not known. However, the initial omega will be the same as the final omega from part 1. So we can say that's equal to omega final from part 1. So if we figure that out, we can use that for the initial omega in part 2. And theta is known. The angular distance covered is 380 radians during the slowdown period. So we don't know any of these other things. And for part B, we need to find the time. So time is something we need to look for. And for part C, what was the acceleration? So these two are what we're looking for in part 2 of the problem, and that's what we're looking for in part 1. So now we have a better idea of how to attack this problem. So going back to part 1, we know omega initial, we know alpha, we know t, we need to know theta, and it looks like our first equation right here is the best one to use. So let's write that one down. So we have theta is equal to theta sub naught plus omega sub naught times time plus 1/2 alpha t squared. We probably can get rid of this because we can assume that at t equals 0, no angular distance was covered. Omega initial is known, so this is equal to 20 radians per second times the time of 3.5 seconds plus 1/2 alpha, which is right here, 25 radians per second squared times the time squared, 3.5 seconds squared. And let's find out. I'll call this theta sub 1. So let's call this, theta sub 1, the amount of distance, angular distance we covered during the first part of the problem. All right, so we have 3.5. We square that times 25 times 1/2. And we add that to 3.5 times 20, which is 70. And so we have 223 radians, radians, total distance covered in part 1. All right. So during part 1 of the problem, when the wheel is speeding up, we cover a total distance of 223 radians. On the way down, when we're slowing down, we cover a distance of 380 radians. So for part A, they want to know what was the total angular distance covered. We can say that's theta 1. Theta total is equal to theta 1 plus theta 2. Theta 1 we just found, 223 radians. Theta 2 was given, that's 380 radians. So that's a total of 603 radians. Total angular distance covered while the wheel was speeding up and while the wheel was slowing down. All right, now we need to find part B and part C, which is the part B, how long did it take? And part C, what was the acceleration when slowing down? So for that, we need to use one of those equations. And let's see here. If I look at this equation right here, the initial omega for the second part of the problem was the final omega from the first part of the problem. And do we know that? We don't, but we could figure that out because we can use what we have here to figure that out. So I'm going to continue by saying omega is equal to omega initial plus alpha t. So what I'm trying to do here is find the initial omega of the second part of the problem by finding the final omega of the first part of the problem. So omega 1 final is equal to this. So that's equal to a startup speed of 20 radians per second plus alpha, which is 25 radians per second squared, times a time of 3.5 seconds. So that would be 25 times 3.5 plus 20. So omega 1 final is equal to 107.5 radians per second. And even though they didn't explicitly ask for that, it will come in handy when we do the second and third part of the problem. So now we can go to look at this equation. We can say that omega final, which will be 0 when it's stopped, equals omega initial, which would be this omega for the second part of the problem, plus alpha, which is the acceleration, which we don't know, that's one of the things that they're asking for, times the time, which we don't know. So we don't know either the time or the acceleration on the second part of the problem. So that equation is not good to solve either one of them because we don't know either the acceleration or the time. So let's look at the third equation. We do know the final omega for the second part of the problem because that's 0, we're stopped. The initial omega will be the same as the final omega from part 1, so we know that. Theta is given. They tell us that we travel under 380 radians, so alpha here is the thing that's not known. And even though that is part C of the problem, it looks like part C is easier to figure out than part B, so let's do part C first. So C, we can use that equation, omega squared equals omega initial squared plus 2 alpha theta. Since we're looking for alpha, we can subtract omega sub naught from both sides and divide by 2 theta. So I can say that alpha is equal to omega squared minus omega initial squared by moving omega initial over to the other side, and then dividing by the 2 coefficients of alpha, which is 2 times theta. Plugging those numbers in, final omega would be 0. Initial omega is the final omega from part 1, which is 107.5 radians per second. And notice that this is squared, so we need to square that. Divide that by 2 theta. 2 times 380 radians, the distance it covers on the slowdown period. So let's figure out what that is. So we square that. Divide by 2, divide by 380 equals 15.2. So this is equal to 15.2. It's minus because it's slowing down, radians per second squared. So that's the answer to part C. At the second part of the problem, when the wheel is slowing down, it's slowing down at an acceleration of 15.2 radians per second squared. So now on to part B, because now that we have the acceleration, the only thing we don't know in this equation here is the time. So using this equation, omega equals omega initial plus alpha t. We're solving this for time, so we can say that time is equal to omega minus omega initial by moving omega initial to the other side and then dividing by alpha. So final omega is 0. Initial omega is the final omega from part 1, which is 107.5 radians per second. And we divide that by alpha, which we just found, minus 15.2 radians per second squared. Now with a calculator, it is 7.07 seconds. And that's the time that it takes for the wheel then to come to a complete stop after the power is done. Wow, this is a really good problem. Notice that we use all three equations of rotational motion, and sometimes it's not always clear which way you want to go, but notice that by looking at each of these equations, see what each of them needs to solve, and see what was given, we were able to figure out what equation to use. And that's not a bad strategy to use on these types of problems. So hopefully this gives you a really good feel for how to work with rotational motions and the rotational motion equations of kinematics. All right, good luck with these. And if you have any more trouble, take another look at these videos, and hopefully they help you conquer the problems in your homework. Good luck with them.